First question. Find the dimensional formula for epsilon naught. We know from Coulomb's law that F equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. We have to find the dimensional formula for epsilon naught. So we could write epsilon naught, we'll take it upstairs, bring force downstairs, and we'll have Q1 Q2 means Q square divided by force times R square. Okay, 4 pi has no dimensions, therefore we don't require to write it. So this is charge. Charge is current into time, so we need to square it. This is current square times square divided by force R square. So if we want to find out the dimensional formula of this quantity, so you know that current square, you could write I or A for the unit of current, general unit of current. Keep it I, say I square. T, we write the general unit of time as capital T, T square. And for force downstairs, we have the dimensional formula M1 L1 T minus 2. And for this is distance square L square. So you could see this is I square. This M goes upstairs, becomes M raised power minus 1. Here L1 plus 2 is L3. This goes upstairs, L raised to the power of minus 3. And T, the power here is 2, and downstairs it's minus 2. So if you bring it up, it adds up to 4. So this is your dimensional formula. I square M minus 1 L minus 3 T4. Okay, let's do the second question. The second question says that a charge of 1 coulomb is placed at the top of your college building and another equal charge at the top of your house. Suppose we have, this is a college building and there is a charge kept here. Its magnitude is 1 coulomb, and there is a house here and there is a charge kept here also. Its charge is 1 coulomb as well. Take the separation between two charges to be 2 kilometers. The separation between these two charges here is 2 kilometers. Find the force exerted by the charges on each other. Okay, so let us find the force on each other. We know that force is equal to, let's assume that the medium here is vacuum or air. Air has roughly the same electrostatic constant as vacuum. So we take 9 into 10 to the power of 9 in SI system. And then product of charges, that is 1 coulomb into 1 coulomb, that's 1, divided by the distance square, that is equal to 2 kilometers, that is 2 into 10 to the power of 3 whole squared. So this is 9 into 10 to the power of 9, and here at the denominator we have 4 into 10 to the power of 6. So we divide 9 by 4, that is equal to 4 2s is 8.2.25 into 10 to the power of 3 newtons. Okay, so this much is the force. There's another part of the question. It says, how many times of your weight is this force? Let us assume that your mass is 50 kilograms. So this is an assumption that we make. So your weight will be equal to m times g. We take g approximately equal to 10, so it's 500 newtons. So if you compare the force between these two 1 coulomb charges with the weight, then you will have, this would be 9 divided by 4 into 10 to the power of 3 divided by 500. Okay, so this is clearly 500 into 2's. This is 2 2's, so this would be 4.5 times. Okay, so the force between two 1 coulomb charges separated by a distance of 2 kilometers is approximately 4.5 times the weight, if you assume the weight of a person to be about 50 kilograms. Okay, let's move forward. Let's do another question. So, at what separation should two equal charges, 1 coulomb each, be placed so that the force between them equals the weight of a 50 kilogram person? So, at what separation should we place two charges so that the force, electrostatic force, is equal to weight of a 50 kilogram person? Okay, so in the previous example we calculated the weight for a 50 kilogram mass, that is mg, that is 50 times 10, that's equal to 500 newtons. Okay, so the electrostatic, for what distance, if we take 1 coulomb charges, two 1 coulomb charges, what should we keep the separation so that the weight is equal to, or the force becomes 500 newtons? So we'll place 500 newtons on the right side, and on the left side we have k, that is 9 into 10 to the power of 9, two 1 coulomb charges, that is 1 into 1 divided by r square. We need to find out this r square. Okay, so you could write implies this, you can take as 9 into 10 to the power of 6 into 10 to the power of 3, that is 1000, is equal to, you take r square upstairs and bring 500 downstairs. This is 500 twos, 9 twos is 18, so 18 into 10 to the power of 6 is r square. So we take the square root of this is r, square root of 18 is this, you can write as 9 into 2, and the square root of 9 is 3, so this is 3 root 2 times square root of 10 raised to the power of 6 is 10 raised to the power of 3 meters. Okay, so you could solve this 3, you could take root 2 as approximately 1.4 into 10 to the power of 3 meters, and that's equal to 4.2 into 10 to the power of 3 meters. Okay, if you want to write it in terms of kilometers, this is approximately 4.2 kilometers. So you should keep two 1 coulomb charges at a distance of 4.2 kilometers, then the separation, then the force between them is 500 newtons, which is the weight of a 50 kilogram person. Okay, let's move ahead to another problem. Two equal charges are placed at a separation of 1 meter. What should be the magnitude of the charges so that the force between them equals the weight of a 50 kilogram person? Now, in this example, we have to calculate the magnitude of the charges. We are given the distance. The distance here is 1 meter. We are also given the force. Force is the weight of a 50 kilogram person that we did in previous two examples, that is 500 newtons. We have to calculate the magnitude of the charges. This is very simple. So you take F, instead of F you will write 9 into 10 to the power of 9, and assume that those two charges have a magnitude Q. So this is Q into Q, that is Q square divided by, what's the distance? 1 meter square, and then that's we have to equate that equal to 500. So when you solve it, this is Q square is equal to 500, that is 5 into 10 raised to the power of, or 5 into 9, this is 10 to the power of, this comes downstairs, this becomes, this is 500 divided by 9 into 10 to the power of 9. So this is Q square is equal to, we'll make it 8, 10 to the power of 8. So we'll keep 90 here. and that is 50 divided by 9, and take that upstairs, that is 10 to the power of minus 8. Okay, so that we can find the square root. Then we find the square root here. Square root of 50. 50 we could write as, once we find the square root of 50, that is 25 into 2. And root of 25 is 5. So this is 5 root 2 divided by 3 into 10 to the power of, if you take the square root of this is minus 4 Coulomb. Okay, so when you solve this, root 2 is 1.4 approximately, multiply by 5 and divided by 3, you will get an approximate number of 2.3 into 10 to the power of minus 4 Coulomb. Okay, let's do the fifth example. It says that find the electric force between two protons separated by a distance of 1 Fermi. This one is simple again. So you have two charges, Q and Q, Q1 and Q2, both equal to the charge on a proton, that's 1.6 into 10 to the power of minus 19 Coulomb. And the distance is 1 Fermi, that is 10 raised to the power of minus 15 meters. And we have to find out the force. So the force would be 9 into 10 to the power of 9 times 1.6 into 10 to the power of minus 19 whole square divided by 10 to the power of minus 15 whole square. This would be in newtons. So this is 9 into 1.6 whole square is 2.56 into 10 to the power of 9 into 10 to the power of this is minus 38 divided by 10 raised to the power of minus 30. This comes upstairs and becomes 10 raised to the power of plus 30. So this is minus, this is 10, so this is 9 into 2.56 into 10. Okay, this is 10 raised to the power of okay, yeah, this is 10, right? Is it? Yeah, we get a 10 here. So we could calculate, this is 25.6 into 9, so 25.6 times 9 is equal to, that's 230.4. So the answer is equal to 230.4 newtons. You could take approximately 230 newtons. Okay. Okay, sixth question. Two charges, 2 microcoulomb and 1 microcoulomb are placed at a separation of 10 centimeters. Where should a third charge be placed such that it experiences no net force due to these charges? So we have a 2 microcoulomb charge here, and we have another charge, 1 microcoulomb charge. They are separated by a distance of 10 centimeters. We're asked, where should we place a third charge so that that charge experiences no net force? Now clearly, if you assume that third charge is positive and place it on the left side, you will see both these charges will repel it towards the left. If you place that positive charge on the right side of 1 Coulomb, you will see that both these two charges will repel that charge towards right. So let's place that charge in between these two charges, because this one is going to left one is going to repel it towards right, and the right one is going to repel it towards left. So it has to be placed somewhere in between. But where? You see, 2 Coulomb charge is going to exert a greater force as compared to a 1 Coulomb charge. So it has to be placed not at the center, not 5 centimeters, but you can guess somewhere beyond 5 centimeters, a little bit towards right. Okay, let's say that we're placing that charge at a distance x from, let's say that charge that we are placing is q, and at a distance x from the 2 Coulomb charge. So what's the remaining distance? That is 10 minus x centimeters. Okay. Now this charge experiences no net force. It means the force exerted by this charge must be equal to the force exerted by this charge on this one. So let us equate those two forces. So the force exerted by this charge is K times 2 microcoulomb times Q divided by the distance square. Distance to this point is x square is equal to, this force must balance the force exerted by the 1 coulomb charge, and that is equal to K times 1 microcoulomb times Q divided by, what's the distance between 1 microcoulomb and that charge? That would be 10 minus x centimeters whole square. So here we see K and K cancels out, micro cancels out, Q and Q cancels out. So we can find out this is 10 minus x divided by x. We could take a whole square here and bring this 2 downstairs. This is 1 divided by 2. Okay. Now we have kept the distance in centimeters only. Okay. So you take the square on this side. This is 10 divided by x minus 1 is equal to 1 by root 2. That is 10 by x is equal to 1 by root 2 plus 1. That's equal to root 2 into 1 plus root 2. So we can flip it to find out x. So x is equal to x divided by 10 is then equal to root 2 divided by 1 plus root 2. And x is root 2. Root 2 is, you can take 1.414 times 10 centimeters divided by, this is 1.414, this is 2.414. So this is equal to 14.14 divided by 2.414 centimeters. Let's see how much is that. Okay, so we have to divide 14.14 divide by 2.414. And we're getting 5.857. That's approximately 5.9 centimeters. Okay. So this is 5.9 centimeters from 2 microcoulomb charge. This should be placed here, or 4.1 centimeters from 1 microcoulomb charge. Okay. Okay, let's look at the next question, 7th question. Suppose the second charge in the previous problem is 1.1 into 10 to the power of minus 6, that is minus 1 microcoulomb. Locate the position where the third charge will not experience a net force. Now, in the previous problem that we've seen, what was the previous problem? We had 2 charges. One was this 2 microcoulomb and another was plus 1 microcoulomb. Instead of plus 1 microcoulomb, suppose we had minus 1 microcoulomb. This is what this problem says. So we have a 2 microcoulomb charge here and the other one at 10 centimeters distance, because 10 centimeters was the distance given in the previous problem. Instead of plus 1 microcoulomb, we have a minus 1 microcoulomb charge. So we need to find out the position where a third charge will not experience a force. Now, clearly, if you were to place a third charge somewhere in between, what's going to happen? Say third positive charge somewhere in between. So this one is going to repel it and this one is going to attract it. So it's not possible that if you place a positive charge or a third charge somewhere in between these two charges, that it will have a net force of 0. So this we rule out. Second, we may take this positive charge on this side. Okay, if we take a positive third charge on the left side of 2 microcoulomb, this 2 microcoulomb is at a closer distance as to this charge, third charge, compared to the minus 1 microcoulomb. So this one is going to exert a greater repulsive force, and minus 1 microcoulomb is going to exert a lesser attractive force. So there will be a net force towards left. So how about a position on the right side of this? Okay, this one is going to exert a force or towards left, and this one is going to exert a force towards right. Here the distance is small, but that distance is compensated by the lesser charge. So this is the correct possibility. Okay, so we assume that we understand that we have to place a third charge on the right of -1 microcoulomb charge. Okay, let us suppose that on the line we place this third charge Q here. At what location? Let's say at a distance x from -1 microcoulomb charge. So the net force acting on this should be 0. Okay, that means the force exerted by +2 microcoulomb charge in this direction should cancel the force exerted by -1 microcoulomb charge. So let us write these two force equations. This one is K 2 microcoulomb times Q, and what's the distance from 2 microcoulomb to this? That would simply be 10 plus x whole square. Okay, this is distance in centimeters. And this force is being balanced by this force, that is the force exerted by -1 microcoulomb charge. So what is that? K times 1 microcoulomb times Q divided by the distance here is x squared. Let's solve it. K goes, microcoulomb goes, and Q goes. So you take this upstairs. This is 2 is equal to 10 plus x divided by x whole square. So you take the square on the other side, it becomes root. So 10 by x plus 1 is equal to root 2. That is 10 by x is equal to root 2 is 1.414. You subtract 1 from that, that is 0.414. And you find out x. X is equal to 10 divided by 0.414 centimeters. Let's see that, how much is that equal to. So if you divide 10 by 0.414 and you get 24.1 somewhere. Okay, this is approximately 24.1 centimeters, okay, from the -1 coulomb charge towards the right. Or you could say this is from -1 microcoulomb charge. Okay, or you could say it's 10 plus 34, that's 34.1 centimeters from 2 microcoulomb charge. Okay, we'll be taking more questions in the next video. Thanks.